So before we go making a program that actually writes something to the console, we need to have a little bit of background about how a processor actually works. In an embedded setting where we don't have an operating system, so if you think of something like a very sophisticated alarm clock, or maybe an alarm system really, if it doesn't have an operating system, it has a processor, but how does that processor actually function? And even though this series of videos doesn't work on embedded technology, I think it's important to realize when the processor starts, it tries to find its first instruction in a memory address. And it doesn't really know where this memory actually is physically, and it really doesn't care. And so what it does is it just reads this first instruction, and then it reads the next instruction, and it reads the next instruction. The instruction tells it to go somewhere else, it will, and if it doesn't, then it just keeps going to the next 32 bits and just reading the next instruction. So when we program in an operating system, we work with the same kind of thought that we start the program and the operating system, when we're not in an embedded environment, hands off these commands to the processor, and in a very simple way says, okay, just execute these commands and let me know when you're done. The way that we let the operating system know that we're done is by using a supervisor call or a system call or a software interrupt. They're all similar. They're all pretty much the same thing, depending on the context. And in that way, we let the operating system know, hey, we need you to take over again. If not, what happens is the program keeps executing code in memory. It keeps adding 4 bytes, 4 bytes, 4 bytes to get these 32 bits. And if it keeps adding and gets to a memory address that it's not supposed to access, if it's an embedded environment, nothing may happen. There may not be an instruction there. If it's in an operating system, ideally what happens is the operating system says, you don't have permission to access this memory space that you're trying to get to. And so I'm going to make sure that this program stops right now. If you're ever using a computer and you get a segmentation fault, this is exactly what's happening, is that the program is trying to access memory that it doesn't have access to, and the operating system is saying, no, don't do that. And so the first thing that we need to do is work on how to actually make a supervisor call and to look at the general layout of the file. And so the first thing that we need to do is we need to have a directive that tells us what's in the file. And we do that by going global. And then this label, this underscore start, is the main function. There's not really functions, but if there were a main function, it's where this underscore start label is. So then we can put that, and the label is just text with a colon after it. And the first thing that we need to do is we need to move values into the registers. And from what the site says is that registers are like little places inside the processor that the processor can actually access directly. You may think that the processor could just write values into memory and manipulate them inside memory, but this isn't true. What has to happen, especially for these processors that have limited instructions, like the ARM architecture, is that we have to pull data from memory, put it in these registers where the processor can actually manipulate them, and then take that data and put it back into memory. So even before we start that, we need to put some data into these registers. Other than reading and writing from memory, what we can do is we can use immediate values. Immediate values are essentially the closest thing that we have to variables. And immediate values are called so because they're immediately available to the instruction. When we get to how these instructions actually break down into the ones and zeros that the computer understands, you'll see that these values are actually in those instructions. So to set up the system call, the supervisor call, we're going to move a number into register 7. And that's simply done by going move And then the registers are 0, 1, 2, 3, 4, 5, 6, 7, 8. They keep going. Unlike some other assembler syntaxes, we don't have EAX, BAX. It's not super confusing like that. They actually have a logical way of doing stuff. And to make an immediate value, we use the number sign, and then we put the value we want. And for now, we'll just do things in decimal because it's easier to think that way, for me at least, unless you're a computer. And we're going to put a note here, and you can see the comments are @ signs. So we'll just say setup exit system call. The next thing that we need to do is, if you look at the sheet of supervisor calls, of system calls, you'll see that the exit call takes one parameter. Well, again, we can't just write exit 0 and be happy. We have to actually put this parameter in the first register, which would be R0. And the code is the error code. Well, we don't have an error in this instance, and so we're just going to put 0 there. So we'll put move, and then R0, and then 0. And then the way that we actually make the supervisor call is by going SVC, and then 0. And so if we run this, the first thing that we need to do is we need to assemble it. And what the assembler does is it turns it into what we just typed into the ones and zeros that the processor will actually understand. And so the assembler is very dependent on the processor. If you're trying to write code for an ARM processor on a machine that uses an Intel processor, then your assembler is probably going to change it into Intel bytecode and not assembler bytecode. So this is why it's important to make sure you're working on a computer that has an ARM processor or know the steps across compile. For the GNU assembler, we need to put an out file, and we'll just put main.o, and then our input file is main.s. If we tried running this right now, it wouldn't work. It doesn't. I mean, we can even add the execute permission on this. Oh, can't type today. And then even try running it, and it doesn't understand. What we need to do is we need to put it into a format that the operating system will understand. And we do this by using a linker. And we invoke it using LD. Our output file we'll just call main. Oh, just call main, and our input file is main.o. And now if we run this file, it does absolutely nothing, which is great. It means there's no error. What we can do, though, is in order to look at the last error code put into the last error code that is returned from an executed program in Linux, is that we can go echo and then $? And we can see that it's 0, and that's our exit code, our error code. If you wanted to change it, you could go back into the program and change it to any number you wanted, pretty much, and that number will be displayed when you try and figure out what the error code for the last program was.